Welcome to the presentation of our project for Big Data Analytics for Healthcare, spring of 2018, by Beena and Michael Chen. We'll walk you through the project background and context, and later talk about the proposed solution. As we move further, we will give details about data extraction, feature construction, and the various machine learning models used. In the end, we will present the comparative results of different machine learning models, and the general motivation for this project is that we want to leverage the massive influx of data, particularly electronic health records, that are coming in. The objective. Mortality prediction is an important topic for public health and has been heavily studied in the past. This project explores machine learning models and compares their performance and mortality predictions for ICU patients during their stay and after their discharge from the hospital. We use big data technologies such as Scala and Apache Spark and Python and Keras. We're also using the Mimic 3 dataset for mortality prediction. The process. For preliminary data analysis, we have uploaded the data to PostgreSQL and analyze the various tables. Here we see a very high-level process of what we did after we took our initial stats. We filtered the dataset to have patients 18 and older, and we removed all rows with null values. We also used, we used ICU stays that ranged between patient's date of death and 365 days prior to the patient's date of death. For the patients that are alive, we calculated the max admit time to the hospital, and then we filter the data up to 365 days prior to this date. Post our analysis, we extracted patient demographics, vital sign measurements, procedures, and lab results during the patient's ICU stay. We further applied aggregate functions like min, max, and mean to derive more meaningful features out of the data. Furthermore, we classified the training samples into three phenotypes: mortality in hospital, mortality 30 days after discharge, and mortality 1 year after discharge. For our first version of implementation, we explored two supervised classifiers, the support vector machine and the logistic regression classifier. We chose to work with them because they produce decent results even with the raw data without aggregation. And here is our results after a few initial iterations. We called it iteration 1. We tried to extract meaningful data from the various mimic tables, such as reading lab events and either taking total counts or average values for these events for feature construction. And you can see the area under RLC curve, the area under precision recall curve, and it'll go up slightly in our second iteration. And the reason being is that we actually took more data from the lab events table and other tables and added them to our data set. What about neural networks? We wanted to leverage the power of neural nets to implicitly capture underlying features. We thought since we had some nice time series data to use, that we could use recurrent neural networks to predict mortality. In particular, we chose to use LSTM cells to build out our recurrent neural net. Here we see a bunch of formulas, and I'm going to give you a brief overview of what they mean. The F means the forget gate. It basically means what do we want to forget from the past. I is the input, it's what do we want to take in from the current input. C is the current cell state, and so that carries over to the next cell. So the C hat is the new, and the C is the what's going to be outputted, right? And CT minus 1 is the old. And O is the output gate. That's going to decide what we're going to output from this cell. And then H is the new hidden state value. Anyways, we converted our data into a data set of time series and ran them through some baseline classifiers, as well as some classifiers of our own. The baseline logistic regression classifier was trained on handpicked features specified in a prior paper, and the baseline LSTM was given 16 hidden states with 2 different LSTM layers. We then tried to use target replication, and we tried to adjust the input using convolutional neural networks to get a better result. Unfortunately, using the CNN didn't help. It actually hurt the results slightly, and using target replication actually helped a bit. Um, the reason for the CNN is probably because we didn't train enough, and we also didn't have enough data. Um, in the future, we would like to extend our work to improve the ROC and precision recall scores. In particular, we would like to introduce bin-based values, excuse me, and score the above indicators based on normal and abnormal values. We'd also like to introduce topic modeling mentioned in Gesemi's paper, and we'd also like to spend more time on tuning the model parameters and tuning the RNN and do a bigger hyperparameter search. Thank you.